Good morning and good afternoon. Thank you for this opportunity to share power packaging trends in emerging 48-volt ecosystems with you. My name is Dr. Ajay Sattu. I am part of Amcor's product marketing team leading the automotive segment. The outline of my presentation will start with a brief introduction to Amcor. Then I'll talk about what's driving power packaging trends in the emerging 48-volt ecosystem in both automotive and non-automotive areas. Finally, I'll present a snapshot of Amcor's automotive portfolio and how we are addressing this market space. A brief introduction of Amcor. Amcor was the pioneer of OSAT business model with more than 50 years of experience. And for the first time in our history, we achieved over 5 billion net sales last year amid COVID-19 pandemic. We have 13,000 employees globally with footprint in 11 countries. We serve several end markets such as communications, consumer, and automotive. Now, allow me to share some key facts about Amcor Automotive. We are number one OSAT by revenue with nearly a billion net sales in 2018 and 2019. We have 11 automotive production locations globally, supplying 40 different package families. Given the safety and mission critical nature of the applications we enable, zero defect quality mindset is a must for us. And in the next few slides, let's look at some key trends and enablers for emerging 48-volt ecosystem. So this chart here shows light vehicle sales forecast and segmentation by degree of electrification. Within the next 5 years, nearly 25% of the cars produced would be electrified and 50% by the end of the decade. Now, one might expect a higher penetration rate given the benefit of electrification. There are several challenges and reasons for this. The first one being cost of the DC battery is prohibitive today. Second, the charging infrastructure that's required would have to be improved significantly. Third, the thermal efficiency of the internal combustion engine is improving. However, what we see on the market today with internal combustion engine cars is that they are somewhat electrified with engine startup systems that reduce emissions by 2 to 3%. These are classified as micro hybrids. However, there are other electrified segments such as mild hybrid, plug-in hybrid, and battery EV that offer better carbon emissions. So let's look at what's driving the proliferation of these electrified cars. Electrification of cars is primarily driven by carbon emission mandates set by various regulatory bodies globally. For example, the chart on the left shows normalized carbon emission for each of the four major auto markets. The solid line shows historical performance, and the dashed line shows the enacted targets over the next decade. The chart on the right shows how carbon emissions can be reduced by various degrees of electrification. ICE is the internal combustion engine with 100% emissions or nearly 100% emissions, whereas mild hybrid uses a smaller motor and a DC battery to aid the internal combustion engine, reducing the emissions up to 15%. On the extreme right, a battery electric vehicle uses a DC battery powering up the motor and thus no carbon emissions. So naturally the question arises, what system requirements are driving the need for a new 48-volt system? So let me talk about a few application areas which are proving to be beneficial from this new 48-volt ecosystem. Today's vehicle power tree is powered directly from a 12-volt lead-acid battery to the mechanical auxiliary loads, which are typically 5 to 7 kilowatt, and these loads are water and oil pumps, climate compressor, headlights, and taillights. However, stricter emission norms and emergence of future power-hungry ADAS systems makes it challenging to improve efficiency. The shift to 48-volt power net enables several benefits, such as wiring harness cross-section reduction and weight reduction. That will generally result in lighter vehicles and also reduced emissions. Now, a second application is cloud computing. So here, one estimate puts as much as 40% of the operating cost of the data center coming from the energy needed to power and cool racks of the servers. Power usage effectiveness and total cost of ownership are very important metrics for data center operators to reduce cost and improve utilization. In terms of power architecture, current data centers are also designed to 12-volt power net. So, like automotive, data centers power architecture also supports a shift to 48 volt. This shift results in higher power density and lower distribution losses. Now, finally, automation for factories and personal care robots are other areas that also support a shift from 24 volts to 48 volt. All these areas have a nice application overlap with existing telecom power supplies which are already at 48 volt. So let's look at automotive 48 volt mild hybrid system and how that can be enabled to improve the carbon emissions. The 48 volt electrical system has become the industry standard for mild hybrid EV applications for several reasons. It's relatively simple to integrate on a vehicle, and it's modular, safe, and compact. The additional system weight is not significant, and finally, the cost to performance ratio is very competitive. The most important function of these systems is energy recuperation. However, the recuperation potential may be different depending on the various powertrain configurations. So let's look at few examples. P0 or the basic configuration is a belt starter generator. Here the motor is connected to ICE with a belt. This is very expensive in implementation and thus also offers limited efficiency improvement. And it's fair to understand that there are losses associated with the belt. Now in P1 configuration, the motor is connected directly with the crankshaft of the ICE. P2 is where motor is side attached to the transmission, and this offers a lot of efficiency improvements but at a higher cost. P3 is where motor is on the gearbox output shaft, and P4 the motor is mounted on the rear axle. P3 and P4 are by far the better recuperation potential configurations. So what you see on the chart here is all of these various applications and their corresponding wattages on the x-axis. So estimates suggest that mild hybrid EVs can reduce carbon emissions by up to 15%, which amounts roughly to 70% the benefit at roughly 30% of the full hybrid system cost. Obviously, willingness to pay an additional $1,500 for a mild hybrid compared to an approximately $4,500 for a full hybrid is the key metric on the cost versus performance trade-offs. Additionally, the 48 volt power net would also serve to provide system readiness or point of load for future applications in both vehicle to everything connectivity or V2X connectivity and ADAS sensors and peripherals. With the mass rollout of level 3 to level 5 self-driving vehicles expected in the next decade, the power requirements for ADAS systems will only surge. Current level 2 capability needs power wattages in the order of a kilowatt, whereas level 4 and level 5 systems would need 10 times more power. Obviously, higher power density packaging solutions will be key to enable this application space. So what I have here is, if we were to break it down and look at individual functional blocks to enable a 48 volt system, whether it's an inverter or a converter, and what's the functionality, right? Whether it's you're converting from DC to AC or DC to DC, and what are the different types of packages that could be applied. So again, here there is need for newer packaging solutions, and also the volume as such for each of these packages, each of these applications is also quite high. So let's look at cloud computing and 5G infrastructure and how that's enabling the 48 volt systems. Today, more than 7 million data centers around the world are needed to manage more than 2.5 quintillion bytes of data, and that is created each day from personal and business uses. 90% of the data was created in the last several years, and this was due to the advent of over the top streaming services, 5G, IoT, and social media. The amount of energy, which is in terawatt hours, consumed globally is on a steady rise over the last decade. Saving a fraction of this energy is substantial. In that regard, OCP or Open Compute Projects was formed to ensure that the data centers, server, rack, and cooling systems are designed in an energy efficient way. From the 5G perspective, 5G networks should be able to handle large amounts of data and large capacity, that is connection density and bandwidth, while also being very reliable, right? And that's edge computing and latency. The key changes with 5G include a greater number of sites and units, meaning higher number of power supplies. With massive MIMO and increased server content, we expect the requirements on the power delivery or conversion to also be aggressive. In terms of power architecture, most data centers today are designed to the 12-volt power net as shown on the left. Like automotive 48-volt system, data centers architecture also supports the shift to 48 volt. The shift results in higher power density, lower distribution losses, higher efficiency, and also deployment flexibility. The benefits at the rack level are obvious, given the reduction in the busbar sizing, number of turbo capacitors, and also lower copper losses. However, the challenge remains how to achieve the voltage conversion from 48 volt to the server board. To power up the central processing unit, CPU cores, and DDR memory blocks, traditionally less than 1.8 volt is required. And also for higher step down ratio, achieving similar conversion efficiencies as before is very challenging. So let's look at what are the other shifting trends. Server boards are also becoming denser to accommodate higher functionality. For example, Intel's data center chip roadmap suggests that its current chip generation VR13 is at 400 watt instantaneous peak power, while the next generation VR13.HC is going to be at 800 watt, while VR14 version is planned to be at around a kilowatt. And shifting power architectures to a traditional two-stage approach using transformer or a direct approach from AC to 400 to 48 volt. To meet the system level congruity, smaller form factor and higher power capable semiconductor packaging is key. Traditional power solutions provide only basic power supply and backup functionalities. They cannot support the deployment requirements of 5G. Therefore, new design concepts are required to drive 5G power solutions. And these principles could be simple, intelligent, and efficient. Now, according to the telecom operators, the power consumption of a single band in 5G can be nearly 3 to 4x that of a 4G with a similar configuration. A 5G baseband unit consumes about 300 watt, while a remote radio head consumes about 900 watt at only 30% load. As more frequency bands are added in the next 3 years, the peak power consumption will increase to about 14 kilowatt, and beyond that, with the addition of millimeter wave, the peak power may increase up to 20 kilowatt. Consistent with the market requirements discussed thus far, there is a need for better power packaging solution. The 48 volt ecosystem presents an opportunity for semiconductor suppliers to apply synergies among these various application segments. Let's look at what some of these examples are in the next slides. From technology trends perspective, for nearly 3 decades, power conversion efficiency and cost have shown steady improvement due to innovations in silicon power MOSFET technologies, power packages, and circuit topologies. Though silicon has been the workhorse, figures of merit such as Ron QG and Ron QSS have reached the theoretical bounds of silicon. Newer material systems such as gallium nitride have entered the market space offering better performance. However, to realize system benefits, packaging technologies must not limit achievable electrical and thermal benefits. Historically, power device packaging has evolved from through-hole packages with long leads to surface mount components with leads such as D2PAC and DPAC. Further, leaded packages have been replaced with leadless surface mount options such as TOL and PQFN. Customers may need solutions that offer effective thermal management via dual side cooling, chip scale packaging, and also multi die integration to reduce parasitics. However, there will be trade offs in terms of cost, performance, and reliability. So let's look at a 48 volt automotive use case. So we are looking at a power stage design for 48 volt bell starter generator application where power electronics are integrated with the motor. Now, as discussed earlier, this requires about 12 kilowatt of power. The inverter stage to power up the motor uses MOSFETs rated higher than 48 volt, while the currents are higher than 500 amps. Generally, multiple MOSFETs are paralleled to meet the full power requirement. So the printed circuit board space is premium, especially because power stage is integrated with the motor itself. Now, D2PAC 7 lead, a common package used in such application and wattage cases, has a package size of nearly 15 by 10 millimeter. Now, similar to D2PAC, TOL, which has got a body size of 12 by 10 millimeter approximately, is a molded package and that has been optimized for high power and also high reliability applications, but it offers much smaller dimensions, right? So nearly 30% smaller dimensions and 50% smaller form fit, allowing for compact designs and also high current capability and lower thermal resistance. In data center power delivery, different power requirements exist for server power supplies in cloud and edge data centers, and also the supply power to CPU cores, DDR memory, and point of load such as standby rails, fans, and drives. For applications where distributed point of load architectures are preferred, a power block or a power stage in a single package is an optimal choice. With flexibility in integration, packages such as PQFN are becoming more popular. PQFN packages offer the scope to improve die to package ratio and exposed heatsink, resulting in higher power density for server power supplies. Larger body size PQFNs offer integration of multiple FETs that either may be a power block. We are die stacking using copper clip technology as shown in PQFN dual stack picture. Another option is to integrate a gate driver with the high side and low side power FETs, which is a power stage, to realize smart power applications such as Dr. Moss, and that is shown as a single stack option. And, and looking beyond what we have discussed thus far, there could be other challenges at the system level that existing packages may fall short. Based on IPC 9701 standard, Toll, for example, can fulfill the standard requirement of 1000 cycles on board. However, mission profiles in end user segments are also changing. Here, extended stress and extended reliability have become a key system requirement. For example, the mismatch between copper lead frame of toll package when placed on aluminum based substrate could lead to higher stress on the soldered material, causing solder fatigue and cracks. By employing a gullwing approach to the toll design, toll G can sufficiently improve the reliability. On the other end, as data center server farms migrate to 48-volt architecture, power density requirements to address power usage effectiveness will be a key concern. The trends of improving power device figure of merit can only take the designers so far. Newer packages such as LF pack in bigger body sizes such as 8 by 8 mm will be a good addition. Compared to a traditional 7 lead D2 pack, an 8 by 8 LF pack is 60% smaller in mechanical dimensions but also 80% lower in volume. Additionally, in both automotive and data center servers, to further improve power density, increasing switching frequency is an option. As such, fast transient response times are demanded by microprocessors anyway. However, the parasitic impedance of conventional power electronic packages operating at frequencies over 1 MHz are not adequate. In this regard, Amcor is exploring chip scale packaging for power transistors, which is the power CSP concept, as shown on the right. This concept is a lead frame based chip scale packaging allowing for double side cooling where the top side can be connected to a heatsink. The bottom side of the package can be mounted to the PCB using thermal vias and power copper layers. Key advantages of power CSP concept is that it eliminates wire bonds and also copper clips, resulting in lower parasitic resistances and stray inductances, thereby reducing conduction losses and switching losses respectively. Finally, allow me to share Amcor's power portfolio that spans across various application segments shown on the bottom of the chart. To the left of the chart, we see various applications such as onboard charger level 1, level 2, DC-DC converters, belt starter generator, data center power, electric axle, and these are all applications that can be enabled with various discrete packages that you see on the screen. Now, as you can see, Amcor has a diverse portfolio that can address the market very well. On the right of the chart, we have the higher wattage applications such as main or traction inverter in hybrid or battery EV. Here, most of the packages used are high power modules, either frame based or molded type. Amcor has developed a dual side cooled molded module for this exact application space. In summary, we can say that it's an exciting time for the engineers working on these emerging areas, and we all look forward to see how this will unfold in the next few years. With that, I conclude my presentation and I'm open for questions. Thank you.